Before I start, I'd like to say that about 4.5 years ago, Yui invited me to a workshop in ISEP on visible light communications. And he rang me up and said, I don't know the first thing about visible light communication. What are we going to present? And I said to Yui, present what you're doing. And Yui presented his work on millimeter wave technologies. And I presented my work on software-defined network and network function virtualization technologies. And we just had a very nice day. And at the end of the day, we all got together and we decided to put a proposal together. And lo and behold, the proposal was a combination of those three technologies that we had got round to presenting. And that's how the project came about, through a workshop in ISEP Paris about 4.5 years ago. And during the project proposal preparation process, we had come up with our sort of concept, which was to provide 5G services indoors, notably in houses and train stations and museums and supermarkets and so on and so forth. And the idea was to provide access through light access points. And these light access points would provide millimeter wave access points as well as VLC access points, and be provisioned by an optical fiber network a ring network that runs throughout the whole home. And because the electronic footprint on these access points was rather small, we conjectured that all the thinking, all the layer processing would occur in the what we call the intelligent home IP gateway, which would do all the intelligent stuff, and that this would be an extension to the 5G network. So this was our concept diagram to get everybody onto the same page. And we identified 4 use cases. The first was a building research establishment home in the their famous integer house, and we came up with a range of different services that could be provided to this integer house through AV streaming, 360-degree headsets, and location became very much part of our objectives. And then we also came up with another use case in a Paris museum, hence ISEP, and we, because the basement of the museum was encased in steel due to water flowing down the hill here, that they wanted some sort of a 5G network in the basement where they couldn't normally access it. I'd like to say that at this point, I'd like to acknowledge the IEEE Broadcast Society for bringing everybody together, because it was Yui, Jian, myself, and the new member was Xun, who came together to put this project together. And if it wasn't for the IEEE Broadcast Technology Society, this would never have happened. So I'd like to acknowledge and thank the Broadcast Society for the role that they played in conceiving this project. And then the third scenario was a Nuevas Ministerial Station platform and tunnel. And this is because 5G signal cannot get down into the tunnel area or in fact the platform area, and they wanted access to 5G signal through the light system and through the millimeter wave, but also in the tunnel for their workers, to access information, and for the managers to reassure the safety of the workers in the tunnel area whilst their operations are going on. And finally, it seemed obvious that it also in supermarkets, so that this would very much benefit from location, based services where, you know, as you walk around the supermarket, you will obtain information about the products, depending on where you are, from the location and media streaming services provided by the 5G network. And we came up with this architecture. It's centered around a RAN, and the RAN is a distributed RAN. It consists of the DRAN and the remote radio light head controller for the upper and the lower parts of the layer 1. And there's a parallel processing pipeline with a layer 2 protocol processor from the software-defined network and network function virtualization server that resides here, that contains all these sort of nice services that can support location, multi-source streaming, security, and all those nice sort of things. And then beyond that are the applications where the home user and museum user and supermarket and train station traveler would be able to access the services from the indoor 5G network. And the remote radio light head controller, we conjectured that should consist of 2 parts. The VLC streaming downlink to things like high definition TVs, 4K and 8K high definition TVs, smartphones and tablets, display screens, VR headsets, and smartphones, but also to have a millimeter wave uplink component, which quickly became an uplink and downlink component, and that there would be one of these remote radio light head controllers per room in the building, with a splitter switch switching to 4, 8, or 16, whatever number of remote radio light head VLC millimeter wave pairs. And so you can have up to 32 of these in a property, so there's plenty of these, and you can have any power of 2 number of remote radio light heads. The innovative products that came from the project was distributed RAN, one of the very first that has ever have been developed in Europe and the world. A PCB horn based and 40 gigahertz horn based antenna, low cost, I would say. 40 gigahertz transceiver module accompanies the module, the antenna module. VLC transmitter LEDs and photodiode receiver LEDs system, and the remote radio light head itself, combining all these 3 technologies within the light system housing, and then the 5G test user terminal, and then the 4K picture-in-picture 5G TV. These are our innovative products that are most innovative hardware products. From the software point of view, from the virtual network functions, multi-source streaming server, follow me TV service, load balancing service, distributed network services, dialer service, sniffing, road scanning, and then indoor location services, artificial intelligence anchor point estimating, and machine learning data fusion. So I just want to highlight the sort of the features of the main innovations of the project, which during the day you'll get more information about. And then finally, the innovative application was a tetherless virtual and augmented reality headsets, location-based data access, location-based data monitoring and guiding, virtual tourism video streaming, multiplayer gaming, and 4K picture-in-picture TV. And the key performance indicator achievements were 42 megabits per second was obtained on the VLC system, with a 10 megahertz bandwidth with 4 QAM and a subcarrier spacing of 30 kilohertz. On the Viavi testbed, a VLC coverage area was 1 square meter, making it suitable for personal area networks. VLC location accuracy, we were able to obtain accuracy of an average 3.5 centimeters, and 80% of all location measurements below 10 centimeters. We were able to get 310 megabits per second to attain on over 100 megahertz bandwidth with 64 QAM, subcarrier spacing of 30 kilohertz on the Viavi testbed, 70 megahertz for a similar sort of setup in the RunEL testbed. The millimeter coverage area was around 2 meters to 6 meters within a room at least. It could have gone further. We could have measured further, but unfortunately we ran out of cable to provide the synchronization signal. And the latencies that we measured was a 0.5 milliseconds from the application physical layer to the gateway physical layer. The latency of much less than half a millisecond was measured. So these were our achievements. The potential, the remote radio line head and the DRAM designs can be enhanced to operate over 400 megahertz for the millimeter wave system with 64 QAM to produce 1.24 gigabit per second remote radio light head controller. And remember, this is per remote radio light head controller. You can have up to 32 of these in a home and provisioned by up to 10 megabits per second for the whole property, because that's what the internal optical fiber network can provide. This 1.24 gigabits per second is scalable, since it can be provided to each of the 32 remote radio head controllers in the room in a building to a total of 10 gigabits per second from a 10 gigabit Ethernet ring home network. The publication achievements, and here again I'd like to acknowledge the support from the IEEE Broadcast Society, because a lot of these journal publications, the conference publications, were through the society. We had 30 peer-reviewed journal publications, 45 peer-reviewed conference publications, 12 public presentations, 3 keynote presentations, 6 invited talks, 9 workshops, 22 exhibitions and demos, 1 cost white paper, and 2 EU white papers on the architecture and vertical services, 3 others in preparation: indoor networks, artificial intelligence, and the mobile edge computing, multi-access edge computing. So I'd like to thank the IEEE Broadcast Society for conceiving this and supporting this. And it's a wonderful society, and any young person attending this young professional workshop, I encourage them to join the society, because it's so supportive of your career, and it would be a really good thing to do to promote your career. It has mine and many others as well. So I'd like to thank Yi Yan Wu and all his team for doing that.